Okay, so good evening, everyone, and welcome to the Frontiers of Parameterized Complexity. Our guest today is Sandor Kisfaludi-Bak, who will speak on Planar Steiner tree with terminals on few faces. Please, Sandor, the floor is yours.
Thank you, Fedor. So first of all, thank you for coming to listen to this talk. And yeah, I was wondering if I should try to give more of a service type thing or just focus on one thing. And in the end, I decided to just talk about one result and try to explain it to a reasonable degree. So if something is not clear along the way, please go ahead and ask. I'm even happy with interruptions. If you are that brave, then do so. And otherwise, the chat should be there. So what I'm talking about today is joint work with Jesper Nederlof and Erik van Leeuwen. And this was a really fun collaboration that we had. So what am I talking about today? The Steiner tree problem is really well known, but just to be on the same page, we are talking about the graph version. So we are given a graph which is undirected, and we have some edge weights. So the edge weights are integers between 0 and capital W. We are also given a set of terminals, which I will denote by capital T. And let's say we have some target value W. And then the question is if there is an edge set S, which connects my terminal set T and has total weight at most W. So in this example, I mean, I could have this as a terminal set, and my terminals will always be these little red circles. And the optimum would be this blue tree that you can see here. It's always going to be a tree. And in this case, it will have total weight 6, which I believe is the optimum in this instance. And the problem is unfortunately quite hard. So the bad news is that, well, it was among the first problems to be shown NP hard by Karp in '72. But then it's not only hard to solve exactly, it's also hard to approximate well. In a factor of 96 or 95, it's hard NP to approximate. It also has no polynomial kernel, and I didn't, so here I'm saying no polynomial kernel. I mean, even for reasonably large parameters, it still doesn't have a polynomial kernel, unless the polynomial hierarchy collapses. So we have a lot of bad news, but still, in the parameterized complexity community, it is known as a very nice problem because it is FPT if the parameter is the number of terminals. And this algorithm predates parameterized complexity by a couple of decades. It's by Jeffers and Wagner, and it is basically a dynamic programming algorithm. So we have these subproblems A of V and Z. So V is going to be a vertex in the graph, and Z is going to be a subset of the terminal set capital T. And then the value of AVZ is going to be the shortest tree, which connects V with Z. And so let's quickly look at how this works. So what we do is we look at basically the branching point in the solution tree that is closest to V. So let's say that vertex is going to be V prime. That's the first place where the tree will branch. And then you can find two subsets of Z. So first subset is Z prime, which will be on one branch from V prime. And the rest of the terminals will be on the rest of the branches from V prime. So this way you can see that the whole tree consists of 3 parts. So first of all, there will be the shortest path from V to V prime. Then there will be the optimum tree with root V prime and terminal set Z prime, and the other optimum tree for the rest of the terminals in Z. And we can immediately see that the number of subproblems will be exponential in the number of terminals, and also the running time will be exponentially the number of terminals, but otherwise, so yeah, basically this is the running time here. And so it's a nice FPT algorithm. And of course, progress did not stop in 1970 on this. By now, we can do this in 2 to number of terminals times maximum wait time and polynomial space. So the previous one used exponential space. We can also do it in the proper weighted setting where the dependence on the maximum weight is only logarithmic. But there the constant is slightly larger, but still polynomial space. And also in terms of approximation, we can do a pretty good job today. There is a 1.39 approximation. So that's roughly the status of the general problem. And when we go to the plane, then well, we have high hopes that the problem becomes easier. So, well, it is still NP hard, and we have known this since Gary and Johnson. But other than that, I mostly have good news. The plane is easier, so we can now approximate to a 1 plus epsilon factor for any positive epsilon, and there is this efficient betas for this problem. There is a polynomial kernel if the size of the solution tree, I mean the number of edges or number of vertices of the tree is the parameter. Although the polynomial is a little bit large. And well, we still have the FPT algorithm, of course, but in addition to that, we also have this sub-exponential XP algorithm by Daniel Marks and the Philipp brothers. So these are very nice results. And there is one particular special case of the planar problem, which has been studied for also a long time. Oh, yeah, sorry. Before I end the good news, I wanted to mention this. Good that it's here. So whereas we have this sub-exponential XP algorithm, we should not expect to have a sub-exponential FPT algorithm because it was shown by in this paper that it would violate the exponential time hypothesis. So that was quite a surprise, I think, for the whole community. But this very important special case is when all the terminals are on the outer face of the planar graph. So let's say that we fix an embedding and all the terminals are sitting on the outer face of the planar graph. So in this case, it turns out that you can solve the problem in polynomial time. And this was already in the 80s observed by Erikson et al. And it's very easy to see why this is the case. So yeah, here's the solution. So all you need to do is to just modify the Dreyfus-Wagner algorithm. Actually, you will not need to look at all subsets of the terminals in this case. And the reason is that if I look at, let's say that I look at the outer face and I number the terminals on the outer face according to this cyclic ordering, then what you can observe is that if I take a root somewhere in the solution tree, then the descendants of any given vertex of the tree will form a subinterval of the terminals. Okay, so for example, yeah, so for example, this could not happen that I have some other terminal sitting here because that would give a crossing. So all we have to care about is this situation where the descendants of any given vertex, the descendant terminals of any given vertex will form a subinterval. And then what you can do is this dynamic program where again we have a vertex V and a subinterval of the terminals X through Y. And then we basically just do the same DP as before. And clearly now I have only polynomially many subproblems, and also I compute each in polynomial time. So this will run in polynomial time. And this is a very nice subroutine, and it has been used both in the kernelization algorithm that I mentioned, and also in the approximation algorithm. So this seems to be an important thing to know. And it also motivates looking at our parameter. So our parameter is going to be the number of faces that you need in order to cover all the terminals. So our setting is going to be the following. I have a planar graph G that has a fixed planar embedding. And I'm also given k faces, which cover the terminals, meaning that all of these terminals are vertices of these k faces. So I will denote by this calligraphic k the set of terminal faces. And now this is a more strict parameter than the number of terminals, because clearly I can always cover size of t terminals with size of t faces. So well, we should expect the problem to become harder compared to the parameterization with the number of terminals. But you can extend the previous algorithm very naturally, when we had only one face to k faces. So all you have to do is to maintain an interval on each face in your subproblem. So the descendants of any given vertex will form intervals on each face. And clearly now you have something like n to the order k subproblems, and you can solve these in n to the order k time. And that's also the space that you will need. So this is a relatively simple XP algorithm. And there was already some work on trying to improve this exponent. I think, so in the 90s, it was improved to 2k plus 2. But unfortunately, it's still a dynamic program, so it is still exponential in k, the space that you need. So what we basically set out to do is to, first of all, decide if this problem is FPT at all with this parameter k, right? Because it was FPT for the number of terminals, so maybe also here it could be. Another question is, if it's not FPT, then can we at least get sub-exponential XP algorithms? And it would also be nice to not need exponential space for all this. So that was my intro, and this is the result that I will try to share today. So we are given the graph G with an embedding, we are given the weighting, the terminals, and we are given k faces which cover the terminal set. Then we can solve the planar Steiner tree problem in 2 to the order k times n to the order square root k time. And we can do so in polynomial space. On the negative side, the problem is W1 hard. It's not going to be FPT probably. And it has no f of k times n to the little o square root k algorithm under the exponential time hypothesis. So this running time, it almost matches the running time of the algorithm. So basically, the exponent of n you cannot improve significantly, but maybe the 2 to the order k is not needed. It's hard to say. Okay, so I mean, this looks like I'm making an assumption about the embedding and being given the faces, but it's not really a big assumption, because already in '88 there was an algorithm where you could find out if such a face cover exists and find an embedding. So if I'm only given the graph G and the terminal set T, and the question is if it has an embedding where I can cover all the terminals with k faces, I can decide that in 2 to the order k times poly n time. So if you want, then you can compose our algorithm with this other one and start with just the planar graph without an embedding. Okay, so that's the result, and now the algorithm. So it took some time to clarify what we wanted here, or how this was going to work. Sorry. And I will already give you the clear picture, I hope. So the way to do this is to find a graph which has low tree width. And the graph that you should consider here is the following. I will take the solution graph S. So that's just the solution tree. It's blue in this picture. And I will also take all the faces, all the terminal faces in calligraphic K, right? So the union of all these edges, I will name that the subgraph H. And I claim that this graph H has tree width order square root K. And I assume that this is the audience where I don't need to introduce what tree width is. So let me just prove this statement. So first, the trivial observation is that if you delete all the faces, all the K terminal faces, then you get a tree, right? Because that's what I just said. It's by definition. But now let's look at the dual graph. So the dual graph will be H star. Deleting edges corresponds to contracting the dual edges. So basically what I said is equivalent to saying that in H star, if I delete the edges incident to these K terminal faces, then I will get a single vertex, right? Because I got a tree, so therefore, so in the primal I got a tree, therefore that was a single outer face. So in the dual, I need to get to a single vertex by doing these contractions. And that means that these terminal face vertices in the dual graph, they actually form a dominating set, right? Because every vertex in the dual will either be one of these vertices or will have to be a neighbor, because after the contraction, they all became one vertex. And now you can use a result by Domain et al., which says that if you have a planar graph of dominating set size K, then its tree width will be at most 15 square root K, which is very nice. And now if you have that, then you can use another result, which says that the tree width of a planar graph and its dual can differ by at most 1. So from that, we get that the tree width of H will be at most 15 square root K plus 1, which is exactly what we wanted to prove. So that's very good. We have a graph of low tree width. So whenever you have low tree width, then you can use separators. So our strategy will be to try and separate this graph H. So I will be looking for some vertex at capital X, which gives, in some sense, a good separation. And so with planar graphs and separators, there are so many forms of separator theorems that it often takes a while to find the version that you need. Luckily, there was a version that we needed already available. So here's what I want to achieve. I want to, first of all, find this vertex at capital X. And here in the picture, I used these green squares to denote capital X. So first of all, I will split the solution tree S into 2 parts, into 4S, basically, which is not surprising. But here's the important part. I want to balance the terminal faces using this split. So after the split, the graph H will have 2 parts, not necessarily connected, but 2 parts. And I want that each part should contain at least K over 3 terminal faces inside. Right? It could be that capital X will cut through some terminal faces. So in this picture, for example, it cuts through this space. I don't really care. All I care about is that I will have at least K over 3 faces contained on this side, and also K over 3 terminal faces contained in the other side. And the reason why this is useful is because then I can say that the forest S1 will avoid at least K over 3 terminal faces, namely those faces that are contained in the other side of the separator. So, so this is super useful. Now the only question is, how are we going to use all this without knowing what the solution is? So we somehow have to map this capital X into the original graph. And the way to do that is here. So, so I will try to guess a lot of things. So first of all, I will start by guessing what the set capital X is. Now I don't have access to H, so I will just guess an arbitrary vertex set from G of size at most order square root k. And then I will know what these vertices are, but of course I don't know where the terminal faces will fall. So I have to guess on which side of the separator each terminal face will end up, right? I need to assign all the terminal faces untouched by X into one of the two sides. And I will also have some terminal faces which I cut through. So those terminal faces will become these, they will be cut up into paths. And for each of those paths, I will guess on which side of the separator it falls. And finally, I have to solve the Steiner tree problem. So when I try to unify the four S1 and S2, I need to get to a tree. So in order to do this well and consistently, I need to know how S1 should connect the vertices of X, and also how S2 should connect the vertices of X. So this you can represent with a partition on the vertices of X, or a subset of X in this case. So this way, I claim that this way you will know enough to solve recursively the problem that you will have for S1 and S2. So basically, what am I looking for with S1? So I'm on one side. I know which terminal faces are there, and also which among the terminal faces that have been cut up, which little paths belong to this part. So basically, I know all the terminals that S1 should cover. And I also know how I should connect to all the vertices of capital X. Right? So this now became an independent problem from the one that I will have for S2. So let's quickly see how this relates to the running time. So the first loop, I will need to repeat n to the order square root k times. That is how many ways I can pick the set capital X. Then for each terminal face, I will have to make a choice to put it on one side or the other of the separator. And when I look at the terminal faces that have been cut up by capital X, where the number of parts that they have been cut up into cannot exceed the size of X. So there will be 2 to the order square root k options there. And finally, when I look at the connectivity patterns or the partitions of X, there are square root k to the order square root k, many of those. And so here you can see that this is larger than this, and this is larger than this. So the significant terms are this n to the order square root k and this 2 to the k. So if you write the recursion, then you will get that to solve the problem with parameters n and k, you will have this many iterations. And the subproblem that you need to solve recursively will have a parameter of at most 2/3 k, right? Because the very important property holds that at least 1/3 of the terminal faces will fall in the other side of the separator. So we do not have any terminals from those. And if you solve this recursion, then you get the desired running time. And also, because this is not a dynamic programming, but we're just doing these loops, you can do this in polynomial space. So this is exactly what we wanted. So are there any questions at this point? So this is basically the algorithm. there is a, well, I swept a few things under the rug, and one is somewhat surprising, and you will see that in the next slide, but I'm curious if there are other questions. If not, then let's.
Maybe I can ask a question. It's not.
Okay.
It's even to the first part of the talk. So there can be many different embeddings of a planar graph on a plane. So
Yes.
how difficult is to find an embedding which covers, which minimize the number of faces covering the terminals?
Yeah, so at some point we kind of talked about, okay, so there's this other algorithm from '88, which does it in 2 to the order k times poly n time, right? So I mentioned this here. And we were actually wondering if we can improve this, right? So I'm talking about this one. We're wondering if we
but this algorithm, it finds the minimum key.
Yes.
Ah, okay.
Yeah. So I mean, given G and T and a value K, decide if there exists an embedding where you can cover with K faces.
Okay. Thank you. Yeah.
Okay, so one thing that I swept under the rug is this one, the base case of this algorithm. It's surprisingly not trivial. So when I do this this separator in the base case, I will end up with constantly many terminal faces. Of course, I cannot use my separator theorem meaningfully anymore on a constant, on a very small constant sized number of faces, terminal faces. And another thing that will happen is we had these separating vertices capital X, and if you're careful, then in the base case you will only end up with a small number of these vertices that come from earlier separations, earlier cuts. So I denote that set by capital B. So still capital B is these green squares, roughly corresponds to X earlier, which I need to connect to. And so the problem that I need to solve in this instance is, okay, I have constantly many faces. I have constantly many of these green boundary vertices. I also have some partition on these boundary vertices. And now I need to find a forest which connects these boundary vertices in the given way and covers all the terminals. And so the natural thing that you would say is, why not just use the basic XP algorithm that we had for the n to the order k algorithm, right? Because now the number of faces is constant. But the problem is that it doesn't work, because the important thing about that algorithm was that so the descendants of any vertex were consecutive on each terminal face. And this is not true anymore. So if you look at this example, I can label all the terminal vertices by the tree that they belong to. So if you look, where am I? Yes. So if you look here, I have this tree A appearing in 2 spots here, but they don't form an interval here, because the tree B is in between here and the tree C is in between, or the other way around. So it's not an interval. Also here, tree C will be weird, right? So you could have a vertex whose descendants will not form an interval. So that's kind of annoying. But what you can observe is that still these labels will not be completely arbitrary. So for example, you cannot have label A, then label B, then label A, and label B again somewhere in the sequence on a given face. So what you can show is that you will have only constantly many distinct intervals on each terminal face. So one tree could have several intervals on a face, but overall the number of intervals on a face will be a constant. Actually, you can give a better bound than this, but it doesn't matter. It should be the number of 4 times the number of trees, actually. So you will have a constant number of intervals per face. You have constantly many faces. So altogether, you need to keep track of constantly many intervals, and therefore you can do a DP in polynomial time. Okay, so with that, I want to finish with the algorithm, and I want to move on to the lower bound. And yeah, I hope that this will be useful. I mean, normally people don't talk much about lower bounds because it's rare that you can generalize. But I think there is some interesting geometry going on here, and I hope that it will be insightful in this case. Okay, so here's the result again, but now we focus on the lower bound part. So we want to prove W1 hardness and this n to the little square root k lower bound. And so if we think back to this larger parameter number of terminals, then we have an FPT algorithm, we have a sub-exponential XP algorithm, and we know that there will not be a sub-exponential FPT algorithm. And so the hardness result, I mean, obviously carries over to a more strict parameter. So we know that we should not expect a sub-exponential FPT algorithm, but that's kind of irrelevant. Now we want W1 hardness. But yeah, I have to say that this is, I find quite interesting. So you have this 2 to the little OK poly and lower bound, and we do have a 2 to the K term in the algorithm, which is kind of a term that you cannot really compare to this n to the order square root K term. So I wonder if this is actually optimal, but who knows? Okay, so how do we prove hardness? Well, if you are in this audience, you probably have heard about the grid tiling problem, but in case you didn't, we are given a k by k grid, and we want to, so in each grid cell, we are given a set of pairs, where a pair consists of 2 integers between 1 and n. A solution to this grid tiling would be to find integers for each row and for each column, such that if I look at any cell, then the pair corresponding to its row and column will be present. So for example, if I look at this set here, then in the row I selected 1, in the column I selected 5. So the pair 1, 5 should be present, and indeed it is right here. So another way to look at this, maybe the more geometric way, is that you have to find a selection from each of these sets, such that if you look at 2 horizontally neighboring cells, then they should agree on their first coordinate. So let's say 3 and 3 here. And also if you look at 2 vertically neighboring cells, then they should agree on the second coordinate. So for example, 4 and 4 here are equal. Okay, and I mean, this is a problem. It's in the parameterized algorithm book, so we know that it's W1 complete, and it has no f of k times n to the low k algorithm under ETH. So basically what we need to get is a reduction from grid tiling, where the number of terminal faces should be order k squared, right? And that will immediately yield this the desired lower bound of f of k times n to the low square root k. Good. So actually we will use a lot of gadgetry from this paper by Daniel Marks and the Page brothers, and this is the first gadget that we will use. So this is a verification gadget. Before I jump in, I have to say 2 important things. So first of all, these vertices here, they are not terminals. They are just important vertices of this gadget. Also, this one is not a terminal. And another important thing is that these edges, they have to be weighted in a very special way. All of these edges will have some integer weights, and actually you can make the whole instance into an unweighted instance just by replacing each edge with a path whose length is its weight, because all these weights will be polynomial in n. But I will now hide all of these weights, so we can just look at the graph itself. And so the purpose of this gadget is to first of all communicate some choice, some integer choice between 1 to n from the left side to the right side. So what I mean by that is that if you want to connect one of these left vertices to one of these right-hand side vertices and also to W, then the minimum way to do that is to pick a horizontal line and this T shape, so the latest vertical line from that. So for example, the weight of this blue set will be the same of any other T shape. So I could also choose this one, for example. It would have exactly the same weight. But any other choice of connecting these would be more expensive. And so, as I said, first of all, this way I can carry an n-ray choice horizontally. But there's a second important thing. That's why it's called the verification gadget. You can choose to delete some of the edges adjacent to W. So let's say if I were to delete this vertex, then this particular choice, namely choosing the second vertex here, Y2, would not work, right? Because I couldn't connect here to W. I would have to choose some more expensive route. Okay, so this way you can do a sort of verification. You can force this horizontal line to be to go through some arbitrary subset of 1 through n. Okay, so that's useful, and you can go one step further. So you could take two of these verification gadgets next to each other and do different restrictions for these W vertices, and that way you could do a check for whether this horizontal line was in one subset of 1 through n or the other subset, and based on that you will connect through W1 or W2. And one more thing before I will make sense of what is happening here. So they also use a so-called connector gadget, and here it actually contains terminals. Yeah, let me skip that. I think I may have made a mistake in this gadget. Yeah, I will skip that. Anyway, this is the one gadget that we don't use, and we generalize it. Yeah, it will not be a problem. So here's our reduction now. So this little triangle that you see here, this is a verification gadget, and that now I will do a reduction from grid tiling. And in this example, I picked k to be 3 and n to be 4. So I will take n copies of the verification gadget next to each other, and then I will take the same thing but flipped 180 degrees, repeated here. And I also have some terminals here, so I will have some root vertex r, and it will be connected to these distant vertices h1, h2, h3 through these long horizontal lines. So let me show you how this is how a solution would look like. All the terminals of the instance, they will be either on the outer face, or they will be in these gadgets F, which I will get into next, because that's, I guess, the most important part here. And so how does this reduction work? Well, if I take the first cell of my grid tiling, it would correspond to this part of the construction. So basically, the height of the blue line will correspond to the first coordinate of the chosen pair, and I will extract the second coordinate of chosen pair vertically using the verification gadget. So the fact that this T shape is in the fourth verification gadget means that in this column I picked the number 4. Okay, so the same way in the next column I will pick it's in the third gadget, so I picked the number 3. And of course, I picked the number 4. I will somehow have to communicate it up and down. Okay, in the top gadget, I don't really need to communicate it up, but here I will need to communicate it down. So I will have again the choice number 4 here, but also symmetrically, I will have the choice number 4 in the flipped gadget. So I hope that the big picture kind of makes some sense. So the hard part is really now to create these gadgets F. And they have to be very special. So they have to communicate an n-ary choice, right? So if I pick, so if this vertex is in the tree, then I want this other vertex to be in the tree. So they basically need to, I need a cheap Steiner forest in these gadgets if and only if they correspond, if they cover 2 opposing vertices. And I need to do this with only one terminal face or constantly many terminal faces. So, so actually in this other construction, they have a way of communicating 1 bit of information using 1 terminal face, but this is not suited for our setting because we have to communicate a choice from 1 through n. So you would need log n of those gadgets, and they don't work. Okay, so basically the challenge is to create these F gadgets, and what they need to do is this. They need to use only constantly many faces and communicate an n-ary choice. Am I making some sense? Can someone ask a question maybe to make sure that we are on the same page? Or so basically, okay, I should say that this tree, I mean, you can see that R is connected to all these H1, H2, H3, and so on. So these F gadgets, they should not do a proper connection. It should really be a forest consisting of 2 trees that somehow oppose each other in a way. Yeah, let's Bart says so far so good. So that I take that as inspiration to move on. So let's now try to forget about all of that for a second and look at this sideways grid where I put some weird edge weights on all the edges. So I took a sideways grid and I cut off the bottom part. And the edges neighboring the bottom vertices, they will have weight 1. And then the edges in the next 2 levels, they will have weight 1/2. The edges in the next 4 levels will have weight 1/4, and so on. You can imagine I do this to infinity. So basically, you can create these layers of exponentially increasing size where the edges have the same weight. And this will somehow be quite useful for us momentarily. But first I have to say where this comes from. And this actually comes from hyperbolic geometry. So, so this, if you're not familiar with the hyperbolic geometry, you can imagine the life of an ant on a lettuce leaf. So the shortest paths that the ant will have to travel from one point on the leaf to another, they will be a hyperbolic metric. And I mean, it's a nice thing to know about, especially when you're constructing gadgets, as it turns out. So the hyperbolic plane has a model called the Poincare half-plane model, and I drew it right here. So what you do is you take the Euclidean plane and you cut off the bottom part. So you only take the points of the plane where the second coordinate is positive. And we will have some very strange metric on this point. So it's not Euclidean distance, but some very different metric. But that's not important for us. What is important is that when you take a point on the x-axis and you do a scaling from that point, then that is an isometry. So what it means is that, let's say if I take this little square and I scale it from the origin by a factor of 2, then I will get this other square. And in the hyperbolic sense, these two objects, the two red objects, they have the same shape and the same size. I can do another scaling. Let's say I scale this second square to this other square in the Euclidean setting. And in the hyperbolic sense, again, I get something of the same size and same shape. So this is very interesting, and you can immediately see how it relates to the grid that you see above. So let's say that I had the origin somewhere here. If I were to scale this edge, then by a factor of 2, then I would get this edge, which also has length 1 altogether. And if I would scale it again, then I would get this path of length 4, but all the weights are 1/4, so it has length 1. And so how is this relevant for us? Well, here's the reason. So let's say that I take 8 or any power of 2 consecutive points in the bottom. And I also take the least common ancestor of the first and last point. So these will be now my terminals. And I take the Steiner tree for these points. Then the Steiner tree for these points will be this nice drawing of a binary tree. This is the unique solution for Steiner tree here for this terminal set. And it's very interesting for several reasons. So actually it is an isometric embedding of this binary tree into this grid. So the distance, for example, from, oh no, sorry, that's an overstatement. It's a quasi-isometry, but anyway, where is my pointer? Yes, here. So if I take this point here, then the distance from this point to this point in the shortest path metric of this graph is actually 2. And this is just one way to realize that shortest path, but also the distance from this point to this point is 2. So it's quite interesting. And what I will actually do is to take a portion of this grid, which can fit 2 such trees next to each other. And I will cut off the top part and the left and right. And I will glue the left, right to the right. Right, so I will glue them this way. And this way you get a gadget called the flower gadget, which is completely symmetric. And all the terminals, they will be in the middle on one face. And what used to be the top vertices, I will call them portals. And in terms of weights, again, I need to blow up the weights so that everything is an integer, and you will have still polynomial weights. So this can be also carried to the unweighted setting. And so the very important thing about this gadget is that if you want a 2-component Steiner forest, which reaches to one of these one of these top portals and also reaches to one of these bottom portals and covers all the terminals, then the cheapest way to do that is to select any pair of opposing vertices, right? And the reason why, well, I cannot prove this because it's a slightly longer proof, but basically these two binary trees in any rotation, they will be the minimum Steiner forest for this instance. And so the whole detour into hyperbolic space was really required because you cannot get anything like this in a Euclidean setting. So if you try to use some kind of grid, then you cannot force a tree to branch exponentially, right? If you have a regular tree, then it wants to branch exponentially, but in a Euclidean setting, it can only branch polynomially somehow. So you really do need some weighting like the one that I mentioned. Okay, so now to put it all together, all we need is to plug in these flower gadgets into these spots, and they will indeed be minimal if you pick opposing vertices to connect. Okay, so the actual proof is somewhat long. You have to balance all the weights within the flower gadget compared to all the weights within the rest of the construction, but you can all do that and you still get a polynomial weighting. So this is, you can make this construction in the unweighted setting as well. And that's the construction. And if we count the terminal faces, well, we have k times k minus 1 flower gadgets, and we have a single terminal face outside. So altogether order k squared terminal faces, which is what we were aiming for. So this shows that the lower bound holds. And yeah, I hope you got something from this. So I want to end the discussion of the lower bound here. I think that the rest of the details are just, yeah, you have to get your hands dirty to do those. So let's not do that and instead talk about some other things. So first of all, what we saw is that you get this 2 to the order k times n to the square root k algorithm. You can do it in polynomial space because it is basically a divide and conquer using separators. But you have to map these separators into G, so that's why you still get this n to the order square root k term, and the 2 to the order k is, well, certainly needed for this algorithm and maybe for all algorithms. For the lower bound, we heavily used the gadget tree from this other paper, but you needed this this hyperbolic idea to make progress ultimately, but it all worked out to get this n to the square root k lower bound. So I have a couple of questions, and I hope that somebody will educate me on these. Maybe some of you will know some of the answers already. So, well, the first question, or the obvious question, is whether there is an n to the order square root k algorithm, but maybe it's not quite a genuine question. So maybe the more interesting question is, can we prove a lower bound that would show that both the 2 to the order k term and the n to the square root k term are needed? I don't think I've seen a lower bound like that. Maybe it exists somewhere. So maybe in this format it could be done. So 2 to the square root k times n in parentheses to the power square root k type of lower bound. I think it could be interesting. And I don't think this is the only problem where this type of running time shows up. So it would be nice to have a technique for these. Now another direction is to forget k as a parameter and just fix k to be 1. We have all the terminals on one face, and you want to, well, you could try to get the best exponent in the plane, but maybe a more interesting question from the parameterized perspective is to look at graphs embedded on surfaces, right? So I have a graph embedded on a surface. All the terminals are on one face, meaning a face that is homeomorphic to a disk. And the question is if well, what is the dependence of the running time on the genus G? Okay, question number 3. I really like unit disk graphs. They are the siblings of planar graphs. And I actually believe that most of the planar lower bounds that we have should also extend into this unit disk setting. But on the algorithmic side, it's much less clear what we can bring there. So maybe the first thing to try would be to get this sub-exponential XP algorithm to work for unit disks. And well, ultimately, it would be nice to get it to work in disk graphs, so the common generalization of planar and unit disk graphs. But that could be somewhat hard. And another way to think about this is to try and define this parameter k at all in unit disk. So it's not clear what we mean by a phase there. But there are also other geometric variants where, for example, convexity can stand in for a phase. So this could be interesting to explore. And yeah, finally, as I mentioned, both the kernelization and the epitas, they use this k equals 1 as a subroutine, but maybe they could use some other reduction with a larger k as subroutine, and with the improved algorithm, perhaps that could lead to improvements either on the kernelization or in the epitas. So that would also be something to look at, I think. And with that, I will thank you for your attention. I hope.
Thank you very much.
We'll have questions.
Thank you very much. So, questions, please.
Hi, I have a question. First of all, thanks for the nice lattice explanation. That was a cool trick for the gadget. Going in a slightly different generalization direction than on your last slide, if we replace finding a Steiner tree, which is a one connected subgraph, by finding a minimum two connected subgraph that spans all the terminals, does it already become NP-hard if the terminals are in a single phase? Do any of your results carry over?
It's a good question. I did not think about it. Yeah, so the short answer is I don't know, but that's actually very interesting. Does someone else in the audience know? I don't know. I certainly don't. No clue.
Okay,
but I will write this. It's a good question. So there are actually other problems studied in this setting that I think there's some flow problems and cut problems. So you are in a planar graph and all terminals are on one phase. This seems to be a popular thing to study. And also, I mean, it does come up as we saw here. It comes up for the kernelization and the approximation. So this could also be interesting, also as a subroutine for other algorithms. Other questions?
A question about bounded genus. So why the approach for bounded genus doesn't work? Because you don't have this separation property.
So with bounded, so actually we didn't try to go into. I mean, we thought about it very briefly, and I think we said that it doesn't generalize too easily.
Okay, maybe I just will try to reconstruct your approach for planar graphs for bounded genus, and we'll see where it breaks. It should break somewhere for sure. Yeah, I mean the separator, maybe it goes through.
Okay, so certainly the simple approach doesn't work because it's obviously not true anymore that the descendants of a vertex will be an interval on the face.
Mm-hmm.
And we are kind of using that. I mean, even in the base case, we are using that in some way. I mean, some bigger way.
Okay.
So you would have to tease that apart at least. But the overall separation approach might go through.
Okay. Thank you. Doesn't look that there are any other questions, and then just let me thank you once again, and I even can clap hands for everyone. Yes, and see you next week. Bye.
Bye, everyone.